गाइस मत करो, बता रहे हैं हम। अभी हम कुछ कह देंगे तो रोने लगना फिर 4 दिन तक, फिर आगे तुम्हारा करियर बर्बाद होने लगेगा। हमसे मत लो, हम बता रहे हैं, अभी तुम्हारा करियर बर्बाद हो जाएगा, तो इसलिए हमसे मत
तो
लो।
हो ही गया ऑलरेडी, अब क्या होगा?
हाँ वो हमेशा हो जाता है।
वही तो।
तो हमसे मत लो, हम बताए हमसे मत बोलो, क्यों बोल रहे हो?
तूने करियर मेरा बर्बाद किया। अब क्या?
हमेशा ही हो जाता है।
अब क्या हुआ? अब
मेरा
क्या?
कुछ होता है नहीं, मैं तुम्हारे से समझो।
और क्या?
मत करो यार, प्लीज मत करो, क्या चाहते हो?
ये क्या कर रही हो? फादर मेरी इसको झाड़ू लगा रही हो। फेंक देंगे उठा के, बता दे रहे हैं। ज़्यादा नौटंकी दिखाओगी हमको। क्या हो गया? हैं? हैं? हेलो? हेलो? रही।
किसी का दिल टूटा, किसी को दर्द पहुंचा।
Do you want to break into top Indian startups? At Mesa,
मत करो बदतमीजी, बता रहे हैं।
अच्छा हटो यहाँ से,
I'm just scared, that's what I'm telling you.
हटो यहाँ से।
क्या दिक्कत है तुम्हें?
हम चल नहीं पा रहे, हमें चलना है।
बाहर जाके चलो ना, कमरे
नहीं, हमें कमरे के अंदर चलना है।
बदतमीजी मत करो मेरे साथ।
तुम किसके साथ करे जाके, बाहर की लड़कियों के साथ करो।
हाँ जाओ करो जाके, हमने नहीं रोक रहे हैं तुम्हें।
देख दो।
भाई हम बता रहे हैं, सुनोगे और तुम बहुत रोगे उसके बाद बता रहे हैं। भाई हम बता रहे, भाई मत करो बता रहे हैं, हम बहुत रोगे उसके बाद तुम कहोगे कि हाँ फालतू में हमने किया, 50 दिन बर्बाद करोगे अपना। हमें नहीं पता है, हमसे मत कहना कि आके तुम्हारा करियर बर्बाद हुआ, ये हुआ वो हुआ।
कह दो, अभी देखिए क्या कहते हैं। कहो देखिए।
अरे हटो ना यार, हट हट कहे दिख नहीं रहा है कुछ कर रहे हैं।
अरे कहो,
कर रहे हो।
कहो, 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 कहो।
हटो गिर जाएगा, गरम है।
नहीं पहले कहो, आज तुम क्या कहो, बताओ 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 क्या कहोगी, हैं? बताओ। ये गाने बंद करो, हम ट्यूटोरियल पढ़ने जा रहे हैं भाई। गाने बंद करो, हम ट्यूटोरियल पढ़ने जा रहे हैं।
ईयरफोन यूज कर सकते
तो ईयरफोन से क्या होता है, बाहर से आवाज नहीं आएगी।
हो। हमें नहीं पता, गाने नहीं बजा।
गाने बंद करो ना, पढ़ने जा रहे हैं, ये कौन सी बात होती
हमारे
है।
गाने स्लो रहे तभी तुम पढ़ने जा रहे हो।
अच्छा हाँ, वो चीज़ हम मजाक कर रहे थे।
इससे पहले तो हमने नहीं सुना ट्यूटोरियल पढ़ रहे हो तुम।
हाँ तो अब हमें नीड है इसलिए हम पढ़ रहे हैं कि वहाँ तुम्हें देख के हम पढ़ेंगे। बंद करो फिर, जल्दी करो, बंद करो ना, बंद। बंद कर दो यार, क्या कर रही हो, क्रिंज देख रही हो।
ये कहो ना क्रिंज लग रहा है तुम्हें।
क्रिंज नहीं लग रहा है हमें।
हाँ हाँ ये कहो ना क्रिंज।
अबे अब देखो ईयरफोन लेके भी बैठे हैं इसीलिए।
ठीक है ना, तो लगाओ ईयरफोन।
भाई तो बाहर तो आवाज जाएगी ना, कानों में नेगेटिव इफेक्ट नहीं पड़ेगा, इतनी ज्यादा साउंड जाएगा। हाँ
नहीं एक दिन में नहीं पढ़ना है, ठीक है।
तुम्हें कैसे पता एक दिन में नहीं पड़ेगा।
हमें पता है एक दिन में नहीं पढ़ेगा।
भाई तुम झाड़ू लगाने से पहले सब बैठ के करती।
तुमसे क्या दिक्कत है?
हमसे कोई दिक्कत नहीं
तो
है।
फिर क्या दिक्कत, क्यों बोल रहे हो?
तो रिमोट लाओ फिर।
भाई मत करो, मेरा हाथ खराब है, तुम्हारे लगा दिए कहीं और फिर कपड़े नहीं है तुम्हारे पास पहनने के लिए, हम बता रहे हैं। हम फेंक देंगे फिर मत कहना हमसे। भाई मत करो बता रहे हैं, मत करो।
क्या इतना क्या नौटंकी दिखा रही हो।
कह रहे हैं मत करो जो।
इतनी नौटंकी क्या दिखा
क्यों
रही हो।
कर रहे हो?
नहीं, हम करेंगे, मेरी माँ ने इतनी नौटंकी क्यों दिखा रही हो लेकिन।
क्यों कर रहे हो, हमको नहीं अच्छा लग रहा है।
तुम्हें तो अच्छे लगे तो क्या होता है, हमें भी बहुत चीजें अच्छी लगती हैं।
हाँ तो तुम नहीं करते हो वो।
फिर तुम क्यों गुस्सा आती हो।
तुम भी गुस्सा हो जाओ, बैठ जाओ जाके, कर क्यों रहे हो?
हम गुस्सा आ जाएंगे तभी तुम्हारी हालत खराब हो जाएगी।
Students get to dive headfirst into the startup ecosystem and get to learn directly from 200 plus startup CXOs and leaders.
Welcome to the Hugging Face course. This course has been designed to teach you all about the Hugging Face ecosystem, how to use the dataset on Model Hub, as well as all our open source libraries. Here is the table of contents. As you can see, it's divided in 3 sections, which become progressively more advanced. At this stage, the first 2 sections have been released. The first will teach you the basics of how to use a transformer model, fine-tune it on your own dataset, and share the result with the community. The second will dive deeper into our libraries and teach you how to tackle any NLP task. We are actively working on the last one and hope to have it ready for you for the spring of 2022. The first chapter requires no technical knowledge and is a good introduction to learn what Transformers model can do and how they could be of use to you or your company. The next chapters require a good knowledge of Python and some basic knowledge of machine learning and deep learning. If you don't know what a training and validation set are, or what gradient descent means, you should look at an introductory course, such as the ones published by deeplearning.ai or fast.ai. It's also best if you have some basics in one deep learning framework, PyTorch or TensorFlow. Each part of the material introduced in this course has a version in both those frameworks, so you'll be able to pick the one you are most comfortable with. This is the team that developed this course. I'll now let each of the speakers introduce themselves briefly.
Hi, my name is Matthew and I'm a machine learning engineer at Hugging Face. I work on the open source team and I'm responsible for maintaining particularly the TensorFlow code there. Previously, I was a machine learning engineer at Parsley, who have recently been acquired by Automatic, and I was a postdoctoral researcher before that at Trinity College Dublin in Ireland, working on computational genetics and retinal disease.
Hi, I'm Lysander. I'm a machine learning engineer at Hugging Face, and I'm specifically part of the open source team. I've been at Hugging Face for a few years now, and alongside my team members, I've been working on most of the tools that you'll get to see in this course.
Hi, I'm Sylvain. I'm a research engineer at Hugging Face and one of the main maintainers of the Transformers library. Previously, I worked at fast.ai, where I helped develop the FastAI library as well as the online book. Before that, I was a math and computer science teacher in France.
Hi, my name is Sasha and I'm a researcher at Hugging Face working on the ethical, environmental, and social impacts of machine learning models. Previously, I was a postdoctoral researcher at Mila, University of Montreal, and I also worked as an applied AI researcher for the United Nations Global Pulse. I've been involved in projects such as Code Carbon and the Machine Learning Impacts Calculator to measure the carbon footprint of machine learning.
Hi, I'm Merve, and I'm a developer advocate at Hugging Face. Previously, I was working as a machine learning engineer, building NLP tools and chatbots. Currently, I'm working to improve the hub and democratize machine learning.
Hello everyone, my name is Lucille, and I'm a machine learning engineer at Hugging Face. To tell you in 2 sentences who I am, I work on the development and support of open source tools, and I also participate in several research projects in the field of natural language processing.
G'day there, I'm Lewis, and I'm a machine learning engineer in the open source team at Hugging Face. I'm passionate about developing tools for the NLP community, and you'll see me at many of Hugging Face's outreach activities. Before joining Hugging Face, I spent several years developing machine learning applications for startups and enterprises in the domains of NLP, topological data analysis, and time series. In a former life, I was a theoretical physicist, where I researched particle collisions at the Large Hadron Collider in CERN.
Hey, I'm Leandro, and I'm a machine learning engineer in the open source team at Hugging Face. Before joining Hugging Face, I worked as a data scientist in Switzerland and have taught data science at university.
Sensu's interactive panel now comes with SenseBoard software, which has shape recognition with measurements,
The pipeline function. The pipeline function is the most high-level API of the Transformers library. It regroups together all the steps to go from raw text to usable predictions. The model used is at the core of the pipeline, but the pipeline also includes all the necessary preprocessing, since the model does not expect text but number, as well as some post-processing to make the output of the model human-readable. Let's look at the first example with the sentiment analysis pipeline. This pipeline performs text classification on a given input and determines if it's positive or negative. Here, it attributed the positive label on the given text with a confidence of 95%. You can pass multiple texts to the same pipeline, which will be processed and passed through the model together as a batch. The output is a list of individual results in the same order as the input text. Here, we find the same label and score for the first text, and the second text is judged negative with a confidence of 99.9%. The zero-shot classification pipeline is a more general text classification pipeline. It allows you to provide the labels you want. Here, we want to classify our input text along the labels education, politics, and business. The pipeline successfully recognizes it's more about education than the other labels, with a confidence of 84%. Moving on to other tasks, the text generation pipeline will autocomplete a given prompt. The output is generated with a bit of randomness, so it changes each time you call the generator object on a given prompt. Up until now, we've used the pipeline API with the default model associated to each task, but you can use it with any model that has been pre-trained or fine-tuned on this task. Going on the Model Hub, huggingface.co/models, you can filter the available models by task. The default model used in our previous example was GPT-2, but there are many more models available, and not just in English. Let's go back to the text generation pipeline and load it with another model, Distill GPT-2. This is a lighter version of GPT-2 created by the Hugging Face team. When applying the pipeline to a given prompt, we can specify several arguments, such as the maximum length of the generated text or the number of sentences we want to return, since there is some randomness in the generation. Generating text by guessing the next word in a sentence was a pre-training objective of GPT-2. The fill-mask pipeline is a pre-training objective of BERT, which is to guess the value of masked words. In this case, we ask the two most likely values for the missing words according to the model, and get mathematical or computational as possible answers. Another task Transformers model can perform is to classify each word in a sentence instead of the sentence as a whole. One example of this is named entity recognition, which is the task of identifying entities such as persons, organizations, or locations in a sentence. Here, the model correctly finds the person, Sylvain, the organization, Hugging Face, as well as the location, Brooklyn, inside the input text. The grouped entities equal true argument used is to make the pipeline group together the different words linked to the same entity, such as hugging and face here. Another task available with the pipeline API is extractive question answering. Providing a context and a question, the model will identify the span of text in the context containing the answer to the question. Getting short summaries of very long articles is also something the Transformers library can help with the summarization pipeline. Finally, the last task supported by the pipeline API is translation. Here, we use a French-English model found on the Model Hub to get the English version of our input text. Here is a brief summary of all the tasks we've looked into in this video. Try them out through the inference widgets in the Model Hub.
If you're a business owner, then animated explainer videos are the best way to capture attention. Get more followers.
So let's talk about the carbon footprint of transformers. Maybe you've seen headlines such as this one, that training a single AI model can emit as much carbon as 5 cars in their lifetimes. So when is this true, and is it always true? Well, it actually depends on several things. Most importantly, it depends on the type of energy you're using. If you're using renewable energy, such as solar, wind, hydroelectricity, you're really not emitting any carbon at all, or very, very little. If you're using non-renewable energy sources, such as coal, then their carbon footprint is a lot higher, because essentially you're emitting a lot of greenhouse gases. Another aspect is training time. So the longer you train, the more energy you use, the more carbon you emit, right? So this really adds up, especially if you're training large models for hours and days and weeks. The hardware you use also matters, because some GPUs, for example, are more efficient than others, and utilizing efficient GPUs properly, so using them 100% all the time, can really reduce the energy consumption that you have, and then once again, reduce your carbon footprint. There's also other aspects such as I/O, such as data, etc., but these are the main 3 that you should focus on. So when I talk about energy sources and carbon intensity, what does that really mean? So if you look at the top of the screen, you have a carbon footprint of a cloud computing instance in Mumbai, India, which emits 920 grams of CO2 per kilowatt hour. This is almost 1 kilogram of CO2 per kilowatt hour of electricity used. If you compare that with Canada, Montreal, where I am right now, 20 grams of CO2 per kilowatt hour. So that's a really, really big difference, almost more than 40 times more carbon emitted in Mumbai versus Montreal. And so this can really, really add up. If you're training a model for weeks, for example, you're multiplying times 40 the carbon that you're emitting. So choosing the right instance, choosing a low carbon compute instance is really the most impactful thing that you can do. And this is where it can really add up if you're training in a very intensive, in a very carbon intensive region. Other elements to consider, for example, using pre-trained models. It's the machine learning equivalent of recycling. When you have pre-trained models available, using them, you're not emitting any carbon at all, right? You're not retraining anything. So that's also doing your homework and kind of looking around what already exists. Fine-tuning instead of training from scratch. So once again, if you find a model that is almost what you need but not quite, fine-tuning the last couple of layers, making it really fit your purpose instead of training a large transformer from scratch can really help. Starting with smaller experiments and debugging as you go. So that means, for example, figuring out data encoding, figuring out, making sure that there's no small bugs that you'll realize, 16 hours into training. Starting small and really making sure that what you're doing, what your code is stable. And then finally, doing a literature review to choose hyperparameter ranges, and then following up with a random search instead of a grid search. So random searches for hyperparameter combinations have actually shown to be as efficient in finding the optimal configuration as grid search, but obviously you're not trying all possible combinations, you're only trying a subset of them, so this can really help as well. So now if we go back to the original paper by Strubel et al. In 2019, the infamous 5 cars in their lifetimes paper, if you just look at a transformer, a 200 million parameter transformer, its carbon footprint is around 200 pounds of CO2, which is significant, but it's nowhere near 5 cars, right? It's not even a transatlantic flight. How it really adds up is when you're doing neural architecture search, when you're doing hyperparameter tuning, and this is trying all possible combinations, et cetera, and this is where like the 600,000 pounds of CO2 came from. So this is really where things add up. So, but if you're doing things mindfully and conscientiously, then your carbon footprint won't be as big as the paper implied. Some tools to figure out how much CO2 exactly you're emitting. There's a web-based tool called the Machine Learning's Emissions Calculator, which allows you to manually input, for example, which hardware you used, how many hours you used it for, where it was located, locally or in the cloud, and then it's going to give you an estimate of how much CO2 you emitted. Another tool that does this programmatically is called CodeCarbon. So you can pip install it, you can go to the GitHub, and essentially it runs in parallel to your code. So essentially you call it, and then you do all your training, and then at the end, it's going to give you an estimate, a CSV file with an estimate of your emissions, and it's going to give you some comparisons. It's got a visual UI where you can really look at how this compares to driving a car or watching TV. So it can give you an idea of the scope of your emissions as well. And actually, CodeCarbon is already integrated into AutoNLP, and hopefully people will be using it out of the box and easily tracking their emissions all through training and deploying transformers.
Are you ready to supercharge your Java coding skills but don't know how? Introducing Lambda.
What is transfer learning? The idea of transfer learning is to leverage the knowledge acquired by a model trained with lots of data on another task. The model A will be trained specifically for task A. Now let's say you want to train model B for a different task. One option would be to train the model from scratch. This could take lots of computation, time, and data. Instead, we could initialize model B with the same weights as model A, transferring the knowledge of model A on task B. When training from scratch, all the model's weights are initialized randomly. In this example, we are training a BERT model on the task of recognizing if 2 sentences are similar or not. On the left, it's trained from scratch, and on the right, it's fine-tuning a pre-trained model. As we can see, using transfer learning on the pre-trained model yields better results. And it doesn't matter if you train longer. The training from scratch is capped around 70% accuracy, while the pre-trained model beats the 86% easily. This is because pre-trained models are usually trained on large amounts of data that provides the model with a statistical understanding of the language used during pre-training. In computer vision, transfer learning has been applied successfully for almost 10 years. Models are frequently pre-trained on ImageNet, a dataset containing 1.2 million of photo images. Each image is classified by one of 1,000 labels. Training like this, on labeled data, is called supervised learning. In natural language processing, transfer learning is a bit more recent. A key difference with ImageNet is that the training is usually self-supervised, which means it doesn't require human annotation for the labels. A very common pre-training objective is to guess the next word in a sentence, which only requires lots and lots of text. GPT-2, for instance, was pre-trained this way using the content of 45 million links posted by users on Reddit. Another example of self-supervised pre-training objective is to predict the value of randomly masked words, which is similar to fill-in-the-blank tests you may have done in school. BERT was pre-trained this way using the English Wikipedia and 11,000 unpublished books. In practice, transfer learning is applied on a given model by throwing away its head, that is, its last layers focused on the pre-training objective, and replacing it with a new, randomly initialized head suitable for the task at hand. For instance, when we fine-tuned the BERT model earlier, we removed the head that classified mask words and replaced it with a classifier with two outputs, since our task had two levels. To be as efficient as possible, the pre-trained model used should be as similar as possible to the task it's fine-tuned on. For instance, if the problem is to classify German sentences, it's best to use a German pre-trained model. But with the good comes the bad. The pre-trained model does not only transfer its knowledge, but also any bias it may contain. ImageNet mostly contains images coming from the United States and Western Europe. The models fine-tuned with it usually will perform better on images from these countries. OpenAI also studied the bias in the prediction of its GPT-3 model, which was pre-trained using the guess the next word objective. Changing the gender of the prompt from he was very to she was very changed the predictions from mostly neutral objectives to almost only physical ones. In the model card of the GPT-2 model, OpenAI also acknowledges its bias and discourages its use in systems that interact with humans.
Stop reading about startups and build one now. Mesa is India's only startup.
Let's study the transformer architecture. This video is the introductory video to the encoders, decoders, and encoder-decoder series of videos. In this series, we'll try to understand what makes a transformer network, and we'll try to explain it in simple, high-level terms. No advanced understanding of neural networks is necessary, but an understanding of basic vectors and tensors may help. To get started, we'll take up this diagram from the original transformer paper entitled Attention is All You Need by Vaswani et al. As we'll see here, we can leverage only some parts of it according to what we're trying to do. We won't dive into the specific layers building up that architecture, but we'll try to understand the different ways this architecture can be used. Let's first start by splitting that architecture into two parts. On the left, we have the encoder, and on the right, the decoder. These two can be used together, but they can also be used independently. Let's understand how these work. The encoder accepts inputs that represent text. It converts this text, these words, into numerical representations. These numerical representations can also be called embeddings or features. We'll see that it uses the self-attention mechanism as its main component. And we recommend you check out the video on encoders specifically to understand what is this numerical representation, as well as how it works. We'll study the self-attention mechanism in more detail, as well as its bidirectional properties. The decoder is similar to the encoder. It can also accept text inputs. It uses a similar mechanism as the encoder, which is the masked self-attention as well. It differs from the encoder due to its unidirectional feature, and is traditionally used in an autoregressive manner. Here too, we recommend you check out the video on decoders especially to understand how all of this works. Combining the two parts results in what is known as an encoder-decoder, or a sequence-to-sequence transformer. The encoder accepts inputs and computes a high-level representation of those inputs. These outputs are then passed to the decoder. The decoder uses the encoder's outputs alongside other inputs to generate a prediction. It then predicts an output, which it will reuse in future iterations, hence the term autoregressive. Finally, to get an understanding of encoders-decoders as a whole, we recommend you check out the video on encoder-decoders.
Welcome to your platform to lead into new worlds.
The atmosphere here today is buzzing. To see the growth, to see the transformation, to see, the appetite to transform even more, and you're seeing that with, conferences and gatherings like LEAP.
In this video, we'll study the encoder architecture. An example of a popular encoder-only architecture is BERT, which is the most popular model of its kind. Let's first start by understanding how it works. We'll use a small example using 3 words. We use these as inputs and pass them through the encoder. We retrieve a numerical representation of each word. Here, for example, the encoder converts those 3 words "Welcome to NYC" in these 3 sequences of numbers. The encoder outputs exactly 1 sequence of numbers per input word. This numerical representation can also be called a feature vector or a feature tensor. Let's dive in this representation. It contains 1 vector per word that was passed through the encoder. Each of these vectors is a numerical representation of the word in question. The dimension of that vector is defined by the architecture of the model. For the base BERT model, it is 768. These representations contain the value of a word, but contextualized. For example, the vector attributed to the word "to" isn't the representation of only the "to" word. It also takes into account the words around it, which we call the context. As in, it looks to the left context, the words on the left of the one we're studying, here the word "welcome," and the context on the right, here the word "NYC," and it outputs a value for the word given its context. It is therefore a contextualized value. One could say that the vector of 768 values holds the meaning of the word within the text. It does this thanks to the self-attention mechanism. The self-attention mechanism relates to different positions or different words in a single sequence in order to compute a representation of that sequence. As we've seen before, this means that the resulting representation of a word has been affected by other words in the sequence. We won't dive into the specifics here, but we'll offer some further readings if you want to get a better understanding at what happens under the hood. So when should one use an encoder? Encoders can be used as standalone models in a wide variety of tasks. For example, BERT, arguably the most famous transformer model, is a standalone encoder model, and at the time of release, it be the state-of-the-art in many sequence classification tasks, question answering tasks, and masked language modeling, to only cite a few. The idea is that encoders are very powerful at extracting vectors that carry meaningful information about a sequence. This vector can then be handled down the road by additional neurons to make sense of them. Let's take a look at some examples where encoders really shine. First of all, masked language modeling, or MLM. It's the task of predicting a hidden word in a sequence of words. Here, for example, we have hidden the word between "my" and "is." This is one of the objectives with which BERT was trained. It was trained to predict hidden words in a sequence. Encoders shine in this scenario in particular, as bidirectional information is crucial here. If we didn't have the words on the right, "is," "Sylvain," and the dot, then there is very little chance that BERT would have been able to identify "name" as the correct word. The encoder needs to have a good understanding of the sequence in order to predict a masked word, as even if the text is grammatically correct, it does not necessarily make sense in the context of the sequence. As mentioned earlier, encoders are good at doing sequence classification. Sentiment analysis is an example of sequence classification. The model's aim is to identify the sentiment of a sequence. It can range from giving a sequence a rating from 1 to 5 stars if doing review analysis, to giving a positive or negative rating to a sequence, which is what is shown here. For example, here, given the two sequences, we use the model to compute a prediction and to classify the sequences among these two classes, positive and negative. While the two sequences are very similar, containing the same words, the meaning is entirely different, and the encoder model is able to grasp that difference.
Hey Kachavi, I am just managing a team of 10 people, man, and it's a complete nightmare for me. How are you managing 50 people in your team?
It's simple. I'm using ChatGPT and AI tools to streamline my work and streamline my team's work as well. And we are projecting we are going to hire 100 more people in upcoming 2 months.
How is that possible? Can you please teach me the same?
Absolutely, I can.
Hi, my name is Aditya Kachwe and I am an alumnus of IIT Kharagpur. I am really passionate about this AI tool. That's why I am conducting this workshop. In past few months, I have researched more than 1400 AI tools and I have found 11 most useful AI tools for every working professional. So I'll be conducting this 2 hours workshop. All these things just at ₹10. And not only this, to make this deal sweeter, I have.
In this video, we'll study the decoder architecture. An example of a popular decoder-only architecture is GPT-2. In order to understand how decoders work, we recommend taking a look at the video regarding encoders. They're extremely similar to decoders. One can use a decoder for most of the same tasks as an encoder, albeit with generally a little loss of performance. Let's take the same approach we have taken with the encoder to try and understand the architectural differences between an encoder and a decoder. We'll use a small example using 3 words. We pass them through the decoder. We retrieve a numerical representation for each word. Here, for example, the decoder converts the 3 words "Welcome to NYC" in these 3 sequences of numbers. The decoder outputs exactly 1 sequence of numbers per input word. This numerical representation can also be called a feature vector or a feature tensor. Let's dive in this representation. It contains 1 vector per word that was passed through the decoder. Each of these vectors is a numerical representation of the word in question. The dimension of that vector is defined by the architecture of the model. Where the decoder differs from the encoder is principally with its self-attention mechanism. It's using what is called masked self-attention. Here, for example, if we focus on the word "to," we'll see that its vector is absolutely unmodified by the NYC word. That's because all the words on the right, also known as the right context of the word, is masked, rather than benefiting from all the words on the left and right, so the bidirectional context. Decoders only have access to a single context, which can be the left context or the right context.